Hello, this video demonstrates the process of making DIY porous media air bearings. We'll look at two configurations, rotary and planar, as well as how you can achieve similar results for your own application. That opaque dark gray surface is a 10mm thick layer of porous graphite, and epoxied to it is this white 3D printed part which is distributing 60 psi shop air through the puck. So submerging the bearing in water is just to demonstrate what's happening. In reality, air bearings work kind of like a fancy hockey table. So if you push that graphite puck against something flat like a granite surface plate, it will create a very stiff cushion of air that allows the bearing to float. All of the air bearings shown in this video cost around $5 in materials to make, where they're actually typically used on much more expensive precision optical components or CMMs. So basically anytime you need to move very small distances on the order of nanometers, air bearings are great because they eliminate stick slip and allow you to move frictionlessly and very precisely. Here are a bunch of different porous materials I've tried for this project. From left to right are an expanded aluminum foam, aluminum oxide, silicon carbide, and then two types of graphite. It seems as though you want a pore size between 0.5 and 1.5 microns, and you really want open porosity, so you want all those pores to be connected, not closed off to one another. I wasn't able to get the aluminum oxide or silicon carbide working because you need a surface grinder with a diamond grinding wheel, which is kind of prohibitive to get them flat enough. I have found examples of people using silicon carbide for air bearings, and here you can see both materials wicking IPA really well, so definitely a very open, porous structure. But unfortunately a little bit harder material to work with without more equipment. So what actually ended up working was Sinker EDM graphite. This attempt was with some generic brand graphite, but there's a lot of nuance to the different grades. What most people think of when they hear graphite is pencil lead, which is actually just graphite dust bonded with clay, so this stuff is much stronger and stiffer. The most readily available brand that seems to work is Poco EDM 3. I bought this box of Sinker EDM cutoffs on eBay for $30 and was able to get plenty of usable stock out of it. So Poco advertises highly isotropic grain structure, and they even sell air bearing specific graphites, so it's possible they just bin the different grades, and there's plenty of overlap in what can be used for what. This planar stage is an example of what you can actually do with a planar air bearing. So you can imagine with one more degree of freedom constrained, you'd have a linear axis for a CMM. There I'm just blowing on the stage, and you can see it takes very little force to move it. On top is just a manifold distributing air to each of the three pucks, which are kinematically mounted with upside down button head socket cap screws. Here's that same stage with a test indicator mounted to it, so it's zeroed with the bearings off, so you can see it's floating on about 40 microns of air, and this is just demonstrating how the bearing can move and really capture the flatness of the surface underneath. Here I'm kind of massaging it, and you can see that the stage isn't especially stiff, and that's because this bearing, the stage is unpreloaded, so for an actual application you'd want to use magnets or vacuum or another opposing air bearing to get a lot more rigidity out of the stage. But in static cases, what air bearings do a very good job of is capturing the flatness of whatever they're floating on, so in this case a surface plate. So generally you could expect that stage to move around with about the same flatness of whatever grade surface plate it's floating on. I was curious about the height and stiffness of the air column, so I ran this test with a force gauge and a test indicator where I'm just manually compressing the bearing until it bottoms out. You can see that within the first 5 newtons of preload, just from the weight of the gauge, we reach about half of the total displacement, so this really demonstrates the importance of preloading these things. I also ran this test with the air cut off to get an idea of how much deflection was coming from the smaller Hertzian deformation of the plenum, which we'd really much rather have made from steel or aluminum for a real application, just because that 3D printed part is compressing so much. The design of the plenum is actually pretty simple. So here is the interface between the graphite and the plenum, and you can see I put those grooved rings in that kind of give you mechanical interference with the epoxy and the chamfer ground into the graphite puck. The pattern that I chose for the plenum was pretty arbitrary, but we just want something that will do a good job of distributing force evenly from the kinematic coupling to the graphite. At the top is an inverse tetrahedron, so this is what gives us 3-point contact for a button head or ball bearing and lets the bearing kind of float into alignment with whatever surface is underneath it. So now we'll talk a little bit about the build process. So this is the 3 pieces of graphite with the 3 printed parts and a couple of NPT fittings. That's the chamfer ground into the graphite, and after epoxying, it just gets lapped with 600 grit sandpaper on a surface plate. This is showing the kinematic contact, so you can see those 3 dots are sort of showing where the different button heads are resting. Here's the one successful attempt I made at a rotary air bearing. So I'm inserting this dowel with a magnet on the end, and there's another opposing magnet in the vise kind of at the front that's causing it to stay suspended there and bounce back and forth. The air bushing was much harder to make than a planar air bearing because it needs to be bored, and you don't get the forgiving lapping process to kind of bring it into circularity. This neat thing happens with air bushings where they'll kind of find their lowest center of mass. So here I'm just kind of spinning it such that the magnet is offset to the top, and just from gravity alone it'll sort of center itself. And you can see that it actually has a lot of radial stiffness here as well, as it's oscillating back and forth and almost leaving the bushing housing. This is just a quick test setup to show how little runout there is between the bushing and the dowel. So that's a 2 micron per division indicator that I'm pushing with a post-it note just to kind of put as little radial load on the bearing as possible. And then I can kind of tap it and you can see that it's definitely in there. Here's a shot of the air bushings, 2 of them that I made at first, with the graphite pressed into the printed part. And here I'm just showing the first thing I tried was just pushing an end mill into the graphite, which creates a lot of play. You really need point contact machining, so like a boring head, which is what's happening here. With this boring operation, I was aiming for 20 microns over the 5/8 diameter dowel pin that I ended up using, and that was found iteratively, and I think the window is probably a little bit smaller than that, but not much larger. So here I'm just using a cylinder gauge to get the inside diameter, which was also a really iterative process. So this is showing all the attempts at creeping up on 20 microns over 5/8. This epoxying method could use a little bit of work, but I just kind of smeared epoxy over the top lip of the graphite and then pressed it fully into the 3D printed plenum. And this was my first attempt that didn't actually work at all. You can see I'm kind of able to spin it a little bit, and it'll glide for a moment and then ground. And I think the problem is that I have 2 things. I have the NPT fitting is coming in at a 90-degree angle, and it turns out that it's really important that air is pushing up and fighting gravity and supporting the pin. The second thing is you really want your plenum to distribute air kind of between the furthest possible points. So if you were trying to support a shaft, the best way to do it would be to spread your bearings as far as possible, and that's sort of the opposite of what's going on here. In this video, I'm showing I glued the 2 bearings that I made together and then rebored that whole stack. So this is what ultimately ended up working and gave me more radial load capacity. Here are just 2 kind of fun experiments in trying to get linear motion out of this air bushing. So here with kind of just a cheap variable power supply, you can kind of move on the micron level with that little wound solenoid kind of attracting and repelling a magnet on the pin. And here is another fun idea for a linear motor where if you seal the bottom cavity, the air pressure kind of forces the pin out. So if you could servo this, you could make a neat linear motor.